This lecture is about the exponential function and e. And so we're constructing, a function that is used everywhere and a number we run into everywhere. So let's start out here. Recall from our previous work that the natural log is a function that takes the positive real numbers into the real numbers, and it's unbounded above and it's unbounded below, and that it is increasing. And so since it is increasing, it is therefore 1 to 1. Okay, so to see that the natural log goes on to the real numbers, suppose that we have a real number. Since the natural log is unbounded above and below, there are numbers a and b such that the natural log of a is less than y and the natural log of b is greater than y. Since the natural log is continuous, the intermediate value theorem guarantees there is an x between a and b such that the ln of x is equal to y. Therefore, natural log is onto, so it's a 1-to-1 onto function, and so its inverse exists. Okay, we will call the inverse of the natural log function the exponential function and denote it exp from the real numbers onto the positive real numbers. Okay, let's look now at a basic property of the exponential function, and it's one that we use a great deal. So suppose we have a couple of real numbers, a and b, and let's say capital A is the exponential of little a, and capital B is the exponential of little b. So by definition we have little a is the natural log of capital A, and little b is the natural log of capital B. So what we can do is just note that the exponential of a plus b is the exponential of the natural log of a plus the natural log of b. Well, the natural log of a plus the natural log of b is equal to the natural log of a times b, which, since exponential is the inverse of log, this is a times b, and so this is equal to the exponential of a times the exponential of b. So exponential transforms addition into multiplication. Okay, so now I'm going to shift gears a little bit, and we're going to talk about limits of functions. We've had limits of sequences. We've not talked about limits of functions. Let's start out with a definition. Let S be a subset of the real numbers, and let A be a real number. We said that A is a limit point of S if for every delta greater than 0 there is an S in the set S such that 0 is less than S minus A in absolute value is less than delta. So this inequality, this three-pieced inequality, is telling us two things. At the bottom end here, it's telling us that S is not equal to A, and at the top end, it's saying that S is close to A. So we can find a point that is close to A, as close as we want to, but is not equal to it. Okay. Now, so what is we've again talked about the limit of sequences. What is the limit of a function at a point? Let f from the set A to the real numbers R be a function, and let little a be a limit point of capital A. We say that L is the limit of f at the point A if for every epsilon greater than 0 there is a delta greater than 0 such that 0 is less than x minus a, since it's 0 less than x minus a less than delta, implies that f of x minus L in absolute values is less than epsilon. In this case, we write the limit as x approaches a of f of x is equal to L. Alright, so we're going to connect the limits of functions with the limits of sequences. We have this theorem. Let f from a set of numbers a into R be a function, and let a be a limit point of capital A. Then L is the limit of f at a if and only if whenever xn is a sequence in x minus the point A that converges to the point A, it follows that the sequence f of xn converges to L. And the proof here goes just the way you would think. And if you're clueless, you need to sit down and think about what this means. You're going to have to just unpack some definitions, maybe look back at where we've done similar things before. Okay, so here we have some basic results. Let A be a subset of the real numbers, and let little a be a limit point of capital A. Suppose that f and g go from capital A to R are functions, such that the limit as x approaches a of f of x is equal to L, and the limit of x as x approaches a of g of x is equal to m. Then the following statements are true. The limit as x approaches a of f of x plus g of x is equal to L plus m. The limit as x approaches a of f of x times g of x is equal to L times m. And if m is not equal to 0, the limit as x approaches a of f of x over g of x is L divided by m. So the first one says the limit of the sum is the sum of the limits. The second one says the limit of the product is the product of the limits. And the third one says the limit of the quotient is the quotient of the limits, provided the denominator limit is not equal to 0. Okay, so proving number 3 here. The others will go similar. Suppose that xn is a sequence in A minus the point A that converges to the point A. Note that f of xn converges to L, and g of xn converges to m. So f of x over n over g of xn converges to L over m. Therefore, the limit as g of x, limit as x approaches a of f of x over g of x is L over m by the result we had in sequences.